This is practice midterm number 3, problems 1 through 21. This is in the comprehensive part of the test. This is going to be the Scantron part of the test where you fill in the bubble. And so the questions, the first 21 questions are all true, false. Classify the following statements as true, A, or B, false. Now, the first question, number 1, the valence bond approach, or it says in the valence bond approach, there exists intra-atomic mixture of atomic orbital wave functions to produce hybrid orbital wave functions with the proper orientation. Okay, that is pretty much the statement of the valence bond approach. The big distinction between the valence bond theory and molecular orbital theory is within the valence bond theory there's intra-atomic mixture of atomic orbital wave function to produce hybrid orbitals which are going to be directed in the right, focused in the right direction in space with the right geometry, the right electron pair geometry for, or to give compounds with the right molecular geometry. And so it's going to give the electron geometry. So it's the intra-atomic mixture of atomic orbital wave functions. That's the valence bond approach. With molecular orbital theory, it's different. We keep pure atomic orbitals on one atom is mixed with pure atomic orbitals on another atom. There's inter-atomic mixture versus intra-atomic mixture. Intra-atomic orbital mixture, valence bond approach. Inter-atomic mixture of orbital wave function, that's molecular orbital theory. So this first one, A, is true. So 1 is A. Number 2, the Pauling electronegativity scale provides a measure of an element's tendency to share bonding electrons. And that, again, is the rationale that Linus Pauling, the rationale for Linus Pauling's approach for electronegativity was an empirical way of measuring the effects of the fact that a bond, a covalent bond where there are shared electrons by 2 nuclei, if they're not shared equally, the one that gets the more than half of the electron density is going to build up a partial negative charge, and the one that gets less than half of the electron density is going to build up a partial positive charge, and that is going to give a dipole in the bond, and a dipolar bond will be stronger as a result of that presence of the dipole, because the positive charge is going to be attracted to the negative charge. And Pauling used that rationale and measured the bond strengths of a series of homologous compounds and noted the strength, the extra strength in the bonds over and above what he called the geometric mean. He measured the bond strength of an AA bond and a BB bond, and then he measured the strength of an AB bond, between the 2 elements, and the excess strength of the bond over and above the geometric mean of the 2 parent bonds was what he used to come up with his scale, the electronegativity scale, which gives the greatest electronegativity to the smallest element. And so that is just exactly what it does. It provides a measure of the amount and the extent to which an element tends to share the electrons in a covalent bond. And that's why the Pauling scale is only going to go up to group 7. The noble gases don't have any electronegativity because they don't form covalent bonds, and the exception to that being xenon. And so number 2 is A. That's true as well. Now, number 3. In oxygen, the repulsive interactions between the sigma 2s orbital electrons and the sigma 2pz orbital electrons drives the sigma 2pz energy above the pi 2p energy. Well, this is false, but why? It's quite the opposite. It is that interaction, and this is depicted here. Here's the sigma 2s sigma bond. It's a sigma bond because there's electron density that lies along the axis connecting the atoms, and it's a 2s because it's constructed out of the parent atomic orbitals of the 2s atomic orbitals. So it is mostly ellipsoidal in shape, and this is the sigma 2pz. This is the this arises from a pz orbital wave function on one atom overlapping with a 2pz orbital wave function on another atom in a bonding fashion. So the sum of them, they overlap in the middle, and this has electron density that is in the same region of space as this occupied orbital, molecular orbital. And so that repulsive interactions trying to place electrons in the same region of space causes this to be higher in energy. It takes more work to place one in. Now, as we proceed across the periodic table, due to the increase in electronegativity as we proceed across a row, the electrons are held more tightly, and with the s electrons in particular, there is less electron density localized in the area region between the nuclei, and it's more localized on the atoms, and we eventually end up with an extreme case where there's very little as we get to the right-hand side of that second row. And so it's more localized on the atoms themselves in the sigma 2s case. Whereas with the p electrons, they have a node at the nucleus, so they are not going to shrink as much, and so it's not going to have the same effect. And so the pi, or the sigma 2pz, is not going to have as much of this effect as the ones constructed out of the 1s or the 2s orbitals, which have significant electron density near the nucleus. So they're going to be held more tightly, and so the energy, the repulsive interaction, is lowered, and this actually drops down the energy of this. And now let's go over here and look at the molecular orbital. The energy of the molecular orbitals. The order of the orbitals is such that for the early second row elements in the homonuclear diatomics, the pi orbitals are going to be the 2p, pi 2p, are lower in energy than the sigma 2p for the reason we just mentioned. And this is true for lithium through nitrogen. Okay? And whereas as we proceed across, we get successively more electronegative, and when we get to oxygen, the energy of the sigma 2pz is actually lower than that of the pi 2p for that very reason. So, in fact, let's go back and now look at the question. The question here was, in oxygen, the repulsive interactions between the sigma 2s orbital electrons and the sigma 2pz orbital electrons drives the sigma 2pz above the pi 2p energy? No. That's the reason it drops down below. It is that interaction, that repulsive interaction, that is the cause of the ordering of the molecular orbitals that is measured experimentally. And so this is false. So the answer to 3 is B. Fill in that bubble on your Scantron and write it on your test as well. Okay. Number 4. there is interatomic mixture of atomic orbital wave functions to produce molecular orbitals. Yeah. This is the same thing we were saying a moment ago about the valence bond approach, where there's intra-atomic mixture. That's how we distinguish. This is one of the main distinctions between the valence bond approach and molecular orbital theory. So that is indeed true. It's consistent with the previous. Now, number 5. The molecular geometry is always the same as the electron pair geometry. Nope. That is absolutely false for the following reason. If the electron pair, if there are no lone pair electrons on the central atom, then indeed the electron pair geometry will be the same as the molecular geometry. But if there are lone pair electrons, one or more, on the central atom, well then those lone pairs are going to occupy a geometric site that is not going to be occupied by an atom. The molecular geometry is the geometric arrangement of the atoms. So since there's not an atom in that site, a lone pair in that site, the molecular geometry and the E-pair geometry are not the same. An example would be ammonia. Let's take methane, ammonia, and water. All 3 of these atoms have 1, 2, 3, 4 electron pairs associated with the central atom. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So they all have to have tetrahedral E-pair geometry. That's the geometry that's going to get all of these electron pairs as far apart from each other while still being associated with the central atom. But in the case of methane, there are no lone pairs on the central atom, so all of these tetrahedral sites are occupied by atoms. So I have a tetrahedral E-pair geometry and I have a tetrahedral molecular geometry. Whereas with ammonia, I've got a lone pair of electrons occupying one of the tetrahedral sites. So the molecular geometry is the geometry of the remaining atoms, and this is trigonal pyramidal, not tetrahedral. And with water, I've got 2 lone pairs occupying tetrahedral sites. And so, in fact, if I was going to try and draw it with the right geometry, I'd have a little wedgie coming out here from this lone pair. And that would be going into the boards. They'd be like this, with the hydrogens out like that for more accurate tetrahedral representation. But here, I've got the molecular geometry that is we call bent. So it's definitely not tetrahedral. And the reason for the difference is because the lone pair electrons occupy one of the geometric sites. And so that's going to give a difference. So which problem was this? Number 5 is definitely false. Now, number 6. A molecule with 4 electron pairs and 1 lone pair on the central atom will have a trigonal pyramidal molecular geometry. Well, I can think of one such case where that's true, and it's going to be true in every such case. Here is a molecule with 4 electron pairs, 1, 2, 3, 4, and 1 lone pair of electrons. And it has trigonal pyramidal molecular geometry. It has tetrahedral E-pair geometry. So number 6 is definitely true. Okay, number 7. Electronegativity increases with decreasing atomic size? Yes, indeed, it does. In fact, that is the reason that we ascribe to the observed Pauling electronegativity scale. As I proceed across a row, I am building, I'm placing valence electrons in above a filled subshell that's the same for all the way across the row. They're all built above the closed shell structure of helium, so that gives the same amount of screening to all the incoming valence electrons. And so as I go across the row, I'm increasing the nuclear charge by 1 proton each, and so that means the valence electrons experience greater and greater positive charge, which is going to hold them tighter, and therefore we get smaller and smaller. And so as we go across the row, so the smallest being fluorine, and the ones that are capable of forming bonds, is given the highest electronegativity, because when the valence electrons are shared in a covalent bond, those shared electrons can approach closer to the fluorine. That means they're going to be held more tightly by the fluorine than they are by the other atom. And that means that it's going to get more than half of the shared electron density. It is going to be more, and that's why it's more electronegative, and the fluorine being the most electronegativity. And now we can talk about the general observation. You can just look at the periodic table when you look at the electronegativities, and indeed the electronegativity goes up as we go across. Has the greatest value, 4 here, 3.5 here, 3 here, 2.5 there, and it goes down as we come down the periodic table. We get larger, and so again, I've got 4, and this is, I believe, 3.5, or actually 3. Sorry, and so, but we see an increase. So the electronegativity, an increase in size and a decrease in electronegativity. Electronegativity gets larger as the atoms get smaller. So, which one was that? And number 7, increases with decreasing atomic size. That is indeed true.